Right, everybody, let's see. For E1-CB mechanism, what is the primary requirement? The requirement is there must be a poor leaving group. So poor leaving group as in like OH, OR, NH2, cyanide, fluoride, this acetylene group, NHR, aldehyde, ester. Have you noticed these are all very strong bases coming from a weak acid? That's why they do not easily break out from carbon bonds. Okay, so that's why it is difficult for them to leave. There will be some kind of a step that need to be followed to push them out of the molecule. Okay, and that's why this mechanism is more recommended. And another thing which is essential for E1-CB is at gamma position, the carb anion group must be present. Okay, which means on gamma position, the carb anion stabilizing group, sorry, a stabilizing group must be present. How is that possible? Let me show you with an example. Got it? For example, here, okay, you can keep writing along with me. Suppose I have a leaving group like fluorine here, but it's a very weak or poor leaving group. But then there is a double bond O here. And now when you treat with a base like let's say ETO minus and heat, correct? You know that removing fluorine is difficult because these are all the poor leaving groups. So what we can do here, the first step would be about extracting the proton from this beta position. You know that this is alpha, beta, and gamma positions. So the first step is always about extracting the proton from beta position, and ethoxide will take the H plus this way. And once you get a carb anion, this carb anion can only be formed if it has some stabilizing group at the gamma position. This is what we meant. That is, resonance stabilization should be offered at the gamma position here like this. Okay, this way we should be able to get the resonance stabilization. Got it? And once you have the carb anion in resonance here, so at one particular instance, when this minus is present, that minus can push here and then remove this fluoride, and thus the elimination is finally favorable like this. And you'll get a conjugated, right, alkene. Got it? Clear? This is the trick that would happen. I hope you understood what is the stabilizing group means here. So we should have this kind of groups in there. Okay. Now let me show you with steps one by one. Okay, you can write it along. This is just to give you an overall idea about how it is happening. Now we'll write with steps one by one. Let's say step one here. You can see first we will have carbon with halogen here and hydrogen here. Okay, and of course there must be some kind of a carbon which will have some stabilizing group like maybe C double bond O or something like this. And this, when you treat with a base, right, the base will extract the proton from this beta position here, and it makes this H minus to leave and get a carb anion here. Okay, so you can see that this will take H plus from here and this will push here. And as it happens, the carb anion is formed. That is the first step. Okay. What is a carb anion, by the way? This plus BH is formed here, isn't it? So, which means basically it is acting like an acid there, correct? Just a right? I'm sorry. So we would have this as K value here. So what we can do, this base will extract H plus and you will get this. So what is this? It is acting like an acid and this is the conjugate base, isn't it? This is the conjugate base. So the equilibrium constant will be equal to the conjugate base concentration into this BH concentration divided by acid concentration into B minus concentration. This is the equilibrium concentration which you will have. So this would be your step one. The step two in this case would be, got it? Once you get this carb anion, this carb anion will try to push the electrons so that the poor leaving group can be coming out. But because poor leaving group will not leave easily, this will take some time. Hence, this is the rate determining step or the slow step. And due to this slow step, now I'll get this as double bond C this way plus X minus. So that's how a double bond is formed here. So notice this is a two-step reaction here and rate of reaction will be equal to some constant into conjugate base concentration. And conjugate base can be written in terms of K equilibrium into acid concentration into B minus concentration, isn't it? Divided by obviously conjugate base concentration. Conjugate base, sorry, divided by BH concentration here. Okay. Yeah, divided by this BH concentration like this. Okay. This will be the rate determining step here. Clear? Which means if you notice the stoichiometry, if you notice the order, it is 1 plus 1 and here it is 1. So that makes it first order reaction. So this will be first order reaction. Okay. And in the slow step, you notice that there is only one molecule involved. Therefore, the type of reaction it is called as E1-CB. E1 because it is one molecule involved in the slow step, and CB is the conjugate base formation. So it is unimolecular conjugate base form that makes this mechanism. Got it? So I hope you guys understood what are the steps that are taking place. Okay. Now, because this is a rate determining step, the stability of carb anion will always influence, correct? The stability of carb anion will influence the rate of the reaction. So we can write that as well. So you can say as a note, you can see stability of carb anion uh, increases with more withdrawing or stronger withdrawing groups at gamma position. So at gamma position, we should have more withdrawing groups here. Or rather, I would have a stronger withdrawing groups like NO2 or something. The rate would be better. Okay. So let me show you examples one by one. Please do it along with me. So first example being phenyl. We have S double bond O, double bond O. Then I have CH with CH2 OPH. O-phenyl is a weak leaving group. So when you react with OH minus here, and I'm expecting a product, so what do we get? So first thing is a carb anion formation, everybody. First thing is a carb anion formation. So you will notice that there is a carb anion forming here. One second. Let me rewrite that. So PHS double bond O, double bond O, then CHH. This will become carb anion, CH2 and OPH. And once you get a carb anion, that will take care of pushing out this group. Hence, we will get PH, S double bond O, double bond O, CH, double bond CH2. This is the product formation. I guess that is clear, everyone. So any cases, if you find this way, you should know it is always going to go via E1-CB mechanism. I'll keep writing more examples. Please do keep working on that. See, NO2 is connected with CH2, then CH2 fluorine. Okay, and this is being treated with OH minus heat. So what do we get? This OH minus can take H plus away from here. The gamma position itself is covered by NO2. That is going to make it more stable because NO2 will have resonance stability. So CH minus CH2F will be formed and this group will be pushed, fluorine will be released out. So what is the product? We will have this as NO2 with CH double bond CH2 plus F minus. That's how E1-CB is observed. Okay. Now, is it always has to be, gamma position always has to be like this? Well, not necessary. For example, if you have something like CH2 and then there is a OH group here and then it is connected with cyanide, for example, and then I'm treating this with, let's say, OH minus. Now, what happens? This OH minus can extract this proton. This OH minus can extract this proton and as it extracts you will get this as O minus CH2 and cyanide. So this O minus can push here to remove out the cyanide and that's how you'll get a formaldehyde C double bond OH and Cn minus. This is also E1-CB type of mechanism, carbanion formation then elimination. Okay, another example, if you have a double bond O and then we have OH group here and let's say there is something like RO minus here or even weaker bases like water will also work. So suppose if you have just the water and heat, water and heat, water can water can also extract the proton from this position and we will get this as double bond O with minus and OH and then this minus will push away, OH will come out and hence we will get this as double bond O and double bond here. That's how you will get an alkyl form. Okay. I hope all of you got an idea how the E1-CB mechanism works. Right, so let me put few more examples here. Suppose if you have a bromine here, correct, and double bond O is at this position. In such case, if at all I'm treating with RO minus and heat, this is a strong base, but double bond O is not at the gamma position. If you may observe, it is at alpha, beta, gamma, delta position. If it is not at gamma position, we will not be able to see the E1-CB type of elimination. Hence, it will be a normal E2 type of elimination. So, double bond will be formed this way, and this will be E2 type of mechanism. This will be E2 mechanism. While on the other hand, if you notice, suppose I have double bond, I have Br here and double bond O here and then I treat this with RO minus and heat. Now here we will not get 100% E1-CB, reason being bromine is a good leaving group. Because bromine is a good leaving group, you will get sufficiently E2 also and E1-CB also. And I would say E2 is still dominant over E1-CB case in this. While the same case, if you had a fluorine group here and then I have a double bond O here and you are expecting RO minus and heat, In this case, we can definitely say double bond and O will be formed. And here, E1-CB is most dominant than E2 type of elimination. Correct? Because fluorine is a weak leaving group. So remember, conceptually, if you have a weak leaving group, this is a problem that you will face. Okay? Everybody, please go through the examples once. If you have any doubt, you can ask me. Right, let's see one by one what are the products you can get. In the first case, you will notice that you'll have double bond O and minus will form here, correct? You have OH, therefore it will finally go for an elimination here with a double bond and double bond O. What is this type of elimination? E1-CB. Okay, same way here also we'll get pH. Fluorine is a weak leaving group. You will get this and we will get double bond here. Okay, and next, if you have this OH and heat here, now there is no gamma group which is going to help the resonance. So it has to forcefully go for E2 elimination. But you know that E2 can give, because there are two types of beta here, E2 can happen here at two positions. One, here like this, a double bond can form. A double bond can form here. This is via E2 mechanism. This one is via E1-CB mechanism. Now this is a Shezhev product, this is a Hoffman product. You know that when you have a weak leaving group, there will be carbanion character developed here. And 1 degree carbanion is more stable. Hence, Hoffman is major in this case. Hoffman is major in this. Now, in the last case, you can notice that again NO2 is present, because of which carbanion can form here, and thereafter we can have a pushing group here. So you can get, sorry, we can get this as NO2 plus Cn minus. So this will happen via E1-CB mechanism. Okay, clear? Next one. If you have OTS is a very, very good leaving group, excellent leaving group, and you have a strong base. So chances are we'll get two types of alkenes here. One is a Shezhev one is a Hoffman one. Now this is the major product here, because OTS is an excellent leaving group. And H2O and heat also, what will it do? Because this is a weak base, this first mechanism is via E2, but here because of weak base, first a carbocation is completely formed. That carbocation will undergo rearrangement, okay? And then on heating, the elimination will take place. So I'll get this product also, I will get this product also. And due to the double bond present here, and this double bond is present here, I will get one more product also. I'm directly writing it. On this side also, I'll get a double bond. Okay. So these three are the products that are expected, out of which this is Shezhev and major. This is Shezhev and major product. So what type of mechanism this is going through? This is going through E1 mechanism. I'm sure all of you are able to recall it. Weak bases usually tend to go for E1. Strong bases tend to go for E2 mechanism. Okay. Here there is a carbanion stability, but at the same time, bromine is a good leaving group. Just now, this is the same question. I have written it earlier. So you know that bromine will go away, double bond will form. Here E2 will be more dominant than E1-CB. And in this case, it will be extremely dominant by E1-CB. So E1-CB is most dominant. You'll hardly see any E2 happening in this case. The last case is also same. RO minus will take H plus from here. Okay. So at this position, you can notice that O minus. Now we have O minus if you take it from this end and we have cyanide, clear? But there is unfortunately it cannot be pushed to make a double bond here or some leaving group is not there here. Since there is no leaving group, this side of the elimination will not take place. Got it? Instead now, what would happen? RO minus will take as if it is a simple E2 mechanism. Correct? So simple E2 mechanism, how does this happen? You'll have like this with OH and double bond plus Cn minus. But this is a poor yield because cyanide is a weak leaving group. It is a poor yield formation. So please do check. Any doubt? Right. See. Next type of elimination is EI elimination. Okay, first we'll do all the type of elimination, then I'll put a lot of, I'll push a lot of questions onto this. Okay, see, EI elimination is also called as sin elimination. So far, we have noticed that E2 elimination will always happen via anti-elimination. That is, leaving group and hydrogen are always anti-periplanar. But now we will be seeing the case where there is a syn periplanar and then elimination is happening. The first of the kind of that example is pyrolysis of esters. Okay, so basically when you have an ester here on heating, you see this part of it. This C2H4 will get elimination and convert into C2H2, and the hydrogen which is present will go along with this oxygen and convert it to acid. Right? This is how typically it will happen. Okay. Now let me show you mechanism. How does this take place? Just on heating, how is it happening here? Check. So first, where you have a oxygen, you try to make it this way. Because we are concerned about these two carbons, I'll first write them. CH2, sorry, uh, yeah, CH2 and H here. Then I have CH2 which is connected with oxygen and that is connected with carbon which is having a double bond O and then this way. This is the kind of reactant which we have. Okay. If I have to put them in terms of numbering, you can see it is 1, 2, 3. This is 1, 2, 3. And here we have this oxygen. So I'll mark that oxygen. This oxygen and this oxygen is the same. Okay. Now on heating, what is observed is that the lone pair present on this oxygen will try to extract the proton from this end. And as it happens so, this bond will break and try to support into a double bond form. And as the double bond forms here, this bond will push into formation of double bond. Eventually, this pi bond will go back on this oxygen. So you can see it is a complete cyclization reaction. So if you have to write the transition state, you can notice that we will have this as CH2, CH2. This bond is breaking. A double bond is being made. This bond is being made with oxygen. And one double bond is converting into single bond. And here oxygen is making into a double bond. And this bond is also breaking. Correct? And this is how the six-membered transition state is happening here. So you can see this is six-membered cyclic transition state. So due to the six-membered cyclic transition state, as it breaks down, you will get this as CH2 double bond CH2 plus we have this as double bond O and OH, propanoic acid. That's how we will get an alkene here. I guess all of you understood how we got the alkene. Yeah. Why it is called syn elimination? Notice this carefully. This hydrogen and oxygen are on the same plane and they are being removed from the same direction. You can see this is also been pulled away, this is also been pulled away from the same direction. So hence, so we can say that since sorry, since hydrogen and OH are removed from same side in a plane, same side of the cyclic plane, it is undergoing syn elimination. Yes, everyone, this is syn elimination. And that syn elimination is what we call it as EI type of mechanism. Okay. Now, check this example, everybody. In this example, what is happening? See, in this example, this is the alpha, beta, and there are two types of beta. That means double bond can form here also. Double bond can form here also. Okay. Let me show you both of them. You know, the way I have shown you this bond breaking, I will try to write the same way for this one also here. See, first case, I can write this as CH2, then we have H, afterwards I have CH, and here I have ethyl, then we have oxygen, then we have double bond O, and this way. Okay. This can undergo elimination where the lone pair from here extracts this hydrogen. This will close into double bond. This will move here. This pi will move here. Correct? By this movement, what type of product you are getting here? The product what you get here is CH2 double bond CH with ethyl, and we will have this as double bond O and OH, which is propanoic acid. Correct? And now I'm writing slightly change here. Now I'm trying to write this one. Notice that we have CH and H here, and there is one methyl group present on it. And then we have CH, another methyl group present on it. Then we have oxygen and a double bond O this way. Okay. Again, I can express the bond breaking here. This will take H plus, it will close double bond, it will close double bond here, and this will take electrons. As it happens from there, you can see it is going to be CH, double bond CH, CH3, and CH3. A cis type of a molecule is formed and propanoic acid is formed. Now it looks like this one is a Shezhev product, correct? Because it has more substitution. This one is a Hoffman product. But the major product is the Hoffman and not the Shezhev. Now, why is that so? Please check this out. When you get this kind of a cyclic structure, right? Cyclic transition state, this will adapt an eclipsed form of conformation between these two carbons. You will have eclipsed conformation because these two are on the same plane, on same side. So this ethyl and this hydrogen should be on the same side as well. Now, one ethyl and one hydrogen will have a less amount of repulsion as compared to that of methyl and methyl undergoing repulsion in the eclipsed form. So therefore, formation of this eclipsed form is less likely to happen as compared to formation of this eclipsed form. Okay. And that's the reason why when it comes to elimination of the esters, pyrolysis of esters, Hoffman's will always be more, will be the major product as compared to that of Shezhev. I suppose the logic is clear, everybody, right? Yeah. Any doubt here? Okay. So I'll just put this as a note here. Sorry, this is 1 and this is 2. Eclipsed conformation of first one is more stable, more stable than second one. Hence, elimination rate is better in first than two. Okay, this is what you need to learn. Make a note quickly. If you haven't written this, please go through it once quickly. What is pyrolysis of esters? Okay, so you can see how it is in say syn periplanar. Due to this methyl repulsions, you will have less likely to form this kind of conformation as compared to that of this conformation. Therefore, Hoffman is major product in this case. Okay. Now let's come to the similar reaction, just like uh, ester pyrolysis. One more type of EI elimination is observed with cope elimination. Cope elimination is observed usually in 3-degree amine oxide. Okay, this is not there for mains, but sometimes it might be seen here and there in advanced cases. So please check this out. So when you have a tertiary amine is nitrogen having three alkyl groups. Okay. So in tertiary amine, when you treat with any peroxide group, this will act like an oxidizing agent and it will oxidize this tertiary amine into this amine oxide form. And now this amine oxide form, which has O minus, correct? If you write the eclipsed form of the same, here you can see nitrogen having two methyl groups like this, having O minus, and one of the molecule here will have CH3, and in that CH3, one of the hydrogens can be taken away by this O, double bond can be closed, and this electron can be removed out. So again, you will get this as a double bond formation. So here also syn elimination is observed, okay, and you will get this kind of alkane formation. So it is also a co-elimination form, okay. So you can see pyrolysis and co-elimination both will give Hoffman product with an EI elimination, everybody. The next type of elimination, which is also going to give you Hoffman elimination, this is called Hoffman exhaustive methylation, HEM. It is also called as HEE, which is Hoffman exhaustive elimination. HEM means via methylation. Okay, got it? That is via methylation. Okay, now let's notice this how we can go through this Hoffman exhaustive methylation case. Got it? See, suppose if you have a 1-degree amine, okay, if you have 1-degree amine, the lone pair present on this nitrogen can push the electrons towards this methyl halide and remove this X minus simultaneously. This kind of a simultaneously attack and removal is called as SN2 mechanism. So the attack and removal will happen and that will give you methyl substitution. Okay. Now you can see the lone pair present on this nitrogen because this X minus which has left will take away this H plus, again leave behind the lone pair. And as long as there is a lone pair, the attack will keep happening again. It will go and attack the second mole. X minus is released. And that X minus will take again this H plus. And this will become a tertiary amine. Tertiary amine can again attack the third mole. remove out this X, and that will become a quaternary ammonium salt. That will become a quaternary ammonium salt. This is quaternary ammonium salt. Once you get a quaternary ammonium salt here, now as you treat with Ag2O moist, when you treat with Ag2O moist, the OH minus can extract the proton from beta position, and NMe3 can be eliminated, just like E2 mechanism. So this is like an E2 mechanism which is happening, through which you can get a double bond form, and tertiary amine will be separated and water will be separated out. Okay. So please check it out once. Then we will do 2-3 questions based on that. Okay. If there is any problem in understanding, you can let me know. See, first, I have this methyl nitrogen group here. So the lone pair present on this nitrogen can again attack on this methyl iodide, removing this I minus. So what is the first structure you will get? In this case, the first structure will be like this: nitrogen this way and one methyl group coming on it. Okay, this is will be A. Again, the lone pair present on nitrogen will make one more attack from here. So it will go and attack one more time with methyl iodide, and that will give you the second mole. The second mole will be like this with two methyl groups on it. Once you get two methyl groups with plus charge here, now there is no hydrogen to leave. So you notice this one. Now, this is very critical part of the reaction here. Check it out. Here, again, I have methyl with plus charge and one more methyl group here. Notice that this is alpha, alpha, beta and beta. Just for you to recall here, remember this. Suppose when you had a fluorine here and then you use some base to eliminate here, I told you that the Hoffman is coming as major. Why is that so? Because fluorine is a poor leaving group. It is not able to leave easily. So it will accumulate some carbanion character here and here. And you know that carbanion is more stable at 1 degree. That is why we said Hoffman is being major. Now, exactly same logic applies here also. NMe plus, this is NR3 plus, is always a weak leaving group. Because it is a weak leaving group, there are two types of beta you can notice. This is a 2-degree beta, this is a 3-degree beta. So it is a 2-degree carbon beta, it is a 3-degree carbon beta. So which can carry more carb anion character? 2-degree can show better carb anion character. And because it can show better carb anion character, so now as the base, which is OH minus, how do we get OH minus? You notice this one. So when you take 2 moles of when you take Ag2O and add it with, H2O, moist. So this will convert into 2 moles of Ag plus and OH minus, 2 moles of OH minus. So basically it is giving an OH minus, and this Ag plus is the one which will take away this I minus and precipitate itself. So I minus, back attack of I minus is not observed because silver is taking care of that. And OH minus, which is a base, will try to extract now. Now, OH minus can extract proton from this position. It can extract from this position. But which is more feasible? This position is more feasible. This position is less feasible because this position is more feasible and this position is less feasible. Why? Because here it is 2-degree carbon, here it is 3-degree carbon, and you know that 2-degree carbanion character is more stable than 3-degree. Therefore, attack will happen and at this position more, and bond will break on this side. And as the bond breaks, what do I get? You will get like this. And we will get a double bond here, and nitrogen will be still present here with two methyl groups and this way. This is the final product you will get, or major product you will get. Okay, clear? So again, this is a Hoffman product, HF product. Please make a note, everybody. Now, let's see what is P1 and P2 in the second example. So first, what is A? A is a methylation that is taking place. After methylation, you will notice that nitrogen will have a methyl here, phenyl here like this. This is A. Okay, this is methyl. And B is two methyls, what you will get it on nitrogen. So we will have this as two methyls with plus charge and phenyl. This is B. And after elimination, you will get a product P1, and the product P1 will be based on the carbanion character. You can see this is alpha, alpha, beta, and beta. Now, in this case, the carbanion at this position is more stable. Reason being, phenyl will stabilize because phenyl is withdrawing group. So, because phenyl is withdrawing group, it will stabilize the carbanion character. So, this beta is more stable than the other beta. Therefore, now the base which you have, let's say OH minus is a base here. So the base will extract proton more easily from this position. Hence, what is the product you will get? You will have nitrogen on this end, but this end you will get a double bond with a phenyl group. So this is P1. And after that, we have C2H5I being added. So again, the lone pair will attack this P1. This lone pair will again attack on ethyl position. So what do I get? Like this with nitrogen, methyl, methyl, and one more ethyl. Here we have double bond with pH. This is the product we got earlier. Okay, and now again it will get positive charge. Clear? Now check this out carefully. We have again two types of beta here. This is the beta, this is the beta. Okay, sorry. This is alpha, alpha, beta, and beta. Okay. So there are two types of beta you can make here. We can make a double bond here, which can make a conjugation on this end. So therefore, this beta carb anion can be more stabilized with this allyl position. Hence, the product that it will form in this case will be like this with a double bond and with a double bond here with a phenyl and plus nitrogen having methyl, methyl and ethyl. So this will become the final product. Please check this out. All okay? Then this is the elimination kind which we'll see. Okay. Now let me put some questions in here. So hope so that you should be able to figure out what is the product in these cases. Okay. See, first example. I have a compound like this, the double bond. Please make a note simultaneously. And I have chlorine here. I'm treating this with H2O and heat. H2O heat means you should think about E1 mechanism. So, if you are making E1 mechanism, question is, find sum of intermediates form and transitions form intermediate transition of the following. Okay, you have to find the sum of intermediates and transition state of the following. Okay, so please check this out. So in such case, what you can do, first you make the carbocation. That will be the first step. So chlorine will come out of it and you will get a carbocation formation. So this is the first carbocation formation, which is the first intermediate. From this intermediate, you can see this is at a secondary position. You can easily go towards this position because it is tertiary position. So 1,2 hydride shift will take place. And due to 1,2 hydride shift, now the positive charge will move on this position. So this is 1,2 hydride shift. Okay. And as you get through the 1,2 hydride shift, again, will it go further 1,2 hydride shift here? Yes, because when it comes here, it will become tertiary plus allyl. So tertiary plus allyl is more stable than only tertiary. So positive charge will again come here. So 1,2 hydride shift. So it will shift to this position again. So once you get to this position here, now you can notice that there will be only resonance stabilization here and there, but intermediate wise, this is the last intermediate you will get. And from here you can get the products, correct? What is a product you can get? I'll just simply write the major product in this case. The major product will be double bond on this side because it will have more substitutions also like Shezef. At the same time, it will have alternative conjugate bond which can help in resonance stabilization. So this will be the major product. Okay. So I hope you understood how the intermediates are formed. What is a product formation? Okay. Now you know that between the intermediate and the reactant, there will always be one transition state. So this is one TS1, TS2, TS3, and TS4. So transition state basically is the number of arrows that you write. So number of transition state are 4, and number of intermediates will be 1, 2, 3. So we have 3 intermediates. So therefore, sum of these two will be sum of transition state and intermediates is equal to 7. This is very standard JE question. You should know how many intermediates and uh, transition states are observed in these cases. Clear? I hope all of you got that. Please make a note of it. And I'm writing the second one. Once you're done, make a note of the second question also. The question is the same. We need to find out the number of intermediates and number of transition state in the following. Sum of intermediates and transition state in the following. Again, this is also an E1 mechanism for your reference. And with the above question, see the next one. How we can start? Again, remove that chlorine from here. So as we remove the chlorine, you will get the stable intermediate as first intermediate, right? So this is the carbocation formation here. So from here to here, this is the first arrow. Okay, and from there 1,2 hydride shift will take place. 1,2 hydride shift will take place, and positive charge will shift here. This is 1,2 hydride shift, and from here this time the ring expansion will take place. See, the bond will break here. This bond will go and attach here. So if I put the numbers here 1, 2, 3, 4, 5, 6. So you can see it is going to form a 6-membered ring. And in that 6-membered ring, the first position has 2 methyl groups on it. So this is carbon 1, 2, 3, 4, 5, 6. Okay. And positive charge is on second carbon. It is on second carbon here. And once you get that, now again you can notice that this is at secondary, and if I methyl shifts, it can become more stable. So 1, 2 methyl shift will take place. Methyl will come here. This methyl will stay. Positive charge will start coming here. And thereafter, now the elimination will take place. Finally, you will get double bond in this position. This is the major product. This is the major product. Okay. Everyone, please check. So how many arrows you can count? 1, 2, 3, 4, 5. 5 arrows, which shows transition states are 5. And how many intermediates are formed here? Intermediates, if you notice, 1, 2, 3, 4. 4 intermediates are formed. Right? So therefore, the summation of transition state plus intermediate is 9. Right? Let's see one more third question of a similar kind here. All right. I have a compound like this, 3-membered ring with methanols on it like this. 3 methanols on it like this. Okay. And this, as you treat with H plus and heat. H plus and heat. Correct. So what is the product that you will get? Let's see how many transition states and how many intermediates we will have in this case. Okay. So question is the same. We need to figure out summation of transition states and intermediates. Right? Everybody with me on that? Chalo. Let's try it together. So first, you can take any one particular position and make it into protonation. So OH2 plus will form first, like this. OH2 plus will form first. and OH2 plus will release the H2O and then convert into carbocation. So directly carbocation nahi banana hai. First you have to make the protonation, then you have to do carbocation. And once you get a carbocation, now you can notice that here chance is this can break and ring expansion can take place. So which is 1, 2, 3, 4. 4 carbons ring expansion can take place. So we will have this as 4 carbon now. Okay. And this is 1 position, 2 position, 3 position and 4 position. On 2 position we have carbocation. Correct? On 2 position we have carbocation. And on 3rd position I have an OH group here. 4th position also I have one OH group like this. Correct? And now notice this one. As soon as this is done, first on heating, you will get a double bond form. So you will get one double bond form here, and we will have this as OH and OH. So is this a final product? No. Basically, this can again undergo protonation because acid is something which you added in sufficient amount. So again protonation will take place. So you will get this as OH2 plus, and here you will have this as OH. Correct? And after protonation, you have to remove this uh, water. So you will get positive charge here, and you will have this as OH. Okay. Now you would notice there is again a chance of ring expansion from here. Correct? Again a chance of ring expansion. So from here the bond will break. So from here the bond will break. This carbon can go and this carbon can go and attack on this position. Okay. Now as it happens here, I'm rewriting this part once again. As the attack take place, it will turn into a 5-membered ring now. So numbering wise, if you notice, this is 1, 2, 3, 4, 5. So this will become a 5-membered ring. So if I put that same numbering 1, 2, 3, 4, 5. So on 5th position, once this is connected from here to here, on 5th position, still I have an OH group present. So we will have this as OH group still present on it. And on the 2nd position, I have a positive charge. And between 3rd and 4th, 5th position, 4th carbon is here. This is 4 and 5. Okay. So as it breaks on 5th position, you have this methanol group. And between 3rd and 4th, I have a double bond like this. Yes. And see, as you start heating it, you will notice that between 1 and 2, you can get a double bond formation. So hence you will get double bond, and then you have methanol here. This can again be protonated, and thus you will have double bond here, and OH2 plus. And this OH2 plus will be lost. OH2 plus will be lost, and you will have this as double bond, and carbocation formation here. And once you get this carbocation formation, again the ring expansion will take place. So bond will break from here, ring will expand. So I can notice 1, 2, 3, 4, 5, 6. So we will end up having again a 6-membered ring here, where between 6 and 1 we have a bond formation, right? On 2 position 3, 4, 5, if you notice between 5 and 6 there is already a double bond. Between 3 and 4 already there is a double bond, and positive charges come on 2nd position. And now as you heat it, the elimination will take place, and thus you will get this as benzene. So final product is benzene, everybody. Okay, final product is benzene. Now count all the arrows here from the starting point, because from here to here is also an arrow. Okay, check. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So how many transition states we have? 12. So 12 transition states we've gone through. How many intermediates we got? Intermediates you can notice from here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we got 12 intermediates as well. So total summation of transition state plus intermediate is 24. You will find a lot of questions in MS Chauhan on a similar cases. You will have this case. Some questions are starting from here. Some questions are starting from here. They all result in only one thing, that is benzene. Okay. Done. I hope the mechanisms are clear. E1, E2, E1-CB, EI, and where they are occurring, what are the cases. Notice, to generalize this, you know that when it comes to E1, E1 is usually favorable by polar protic solvent as a base. And Lewis acids like P4O10, Al2O3, P4O6, they also on heating perform E1 mechanism on alcohols, and they will give Shezef without rearrangement. Like this P4O10, it will remove this, double bond will form, that will be the major product. And with H2SO4, H3PO4 at around 350 degrees, you will have Shezef with rearrangement, that is also E1. And if you have Al2O3 with pyridine, if you take pyridine at around 350 degrees, now it will form Shezef but without rearrangement. Earlier, these were all with rearrangement. This is without rearrangement. Without rearrangement is it will usually go for E2 mechanism. And thorium dioxide and heat usually prefers to go for E2 elimination, but the major product is Hoffman kind. The major product is Hoffman kind. So let me show you with this example here. For example, in the case of H2SO4, it will follow E1 mechanism. So hence, you will have a carbocation here. From that carbocation, the ring expansion can take place. So that will give you this way with positive charge here, correct? And that positive charge can be further migrated back to the tertiary position. And that's when the major product will form by making an elimination. So that's how you'll get a double bond here. So this is major. And next, if you take Al2O3 and heat also, same product will form. Same as above. But same as above. But if you take Al2O3 with pyridine, in the case of pyridine, what happens? Now you don't have to make a carbocation, directly elimination, but Hoffman kind, Shezef kind. So you'll have this one as well as this one. But out of these two, this is Shezef, this is Hoffman. And you know that Shezef is major in this case. Okay. And the last case here, you will notice that the products are the same here, but this time Hoffman is major. So this time Hoffman is major. Clear? So this is summary on the alcohol parts. When you have an alcohol part, which are the reagents which we can use it for E1 or E2, and what are the temperature conditions here. Make a note, everybody. If you have the pre-notes, please try to write the products here. We are done with the mechanism part now. We are going back to the preparation again, just to show all the preparation reactions of alkenes one by one. Check. From alkyl halides, we learned that using alcoholic KOH, we can get a product of alkenes as a double bond here and double bond here. This is Shezef, this is Hoffman, and Shezef is major product. If you take ETOH, this is a weak base favors E1 mechanism. So carbocation is formed. It is already at a stable carbocation form. So it can get a double bond here or it can get a double bond here. This is Shezef, this is Hoffman, and this will be major. Okay. From alcohols, we learned that if only concentrated H2SO4 used and the temperature is greater than 430, then the alkene will be formed. Okay. Mechanism wise, if you notice, first OH plus, proton. When you add the proton, you will start getting this as OH2 plus. Okay. And OH2 plus, when you are heating it, correct, directly HSO4 minus can extract the proton from here. Because primary is not stable, you will get this as a double bond form. Okay. You will get this as double bond form. Got it? Clear? Here, I would like to show one case. Achha, I have written it here already. So first let me finish this one and then I'll write that. So in this case also, if you notice, first carbocation can easily form because it is at secondary position. Then I'll get two products, double bond here or double bond here. So this is Shezef, this is Hoffman, and Shezef is major. And this is happening via E1 mechanism. Now notice this last case. This is a 1 degree carbon, right? So because it is a 1 degree carbon, we expect it is difficult to form carbocation. It is difficult to form carbocation. So we know that HSO4 minus can extract proton from here and that will help making a double bond. Okay, by removing this. This is via E2 mechanism. But problem what happens is, let me take this part back here. Okay, I'll write down that here. Correct. So that is when you have this double bond in the presence of concentrated H plus and heat, again the protonation will take place. So this time protonation will make it, H to add on this position and get a positive charge here. This is following Markovnikov's rule. Following Markov rule. So Markov rule is followed and you get a positive charge. Now this positive charge can further undergo rearrangement to get positive charge on tertiary position. And once you get tertiary position, then you will make a double bond on this position. Therefore, from here, I'm directly writing the steps. Here, what is the product form? The final product will be this one. This is the major product. Okay. So I hope all of you understood this logic. So first E2 will happen and a double bond is formed. And the double bond will get protonation and this time again E1 will happen. Okay, sorry, here. E1 mechanism, you will see elimination will again occur. Now this time protonation is avoided because if you add many proton, you will not get any product again. So therefore, the double bond will keep shifting towards the most stable position. Up to that, the protonation will keep happening. Right? This we already learned, Al2O3, THO2, what will happen. Now notice if you want to get uh, alkenes from aldehydes and ketones, then we use something called Wittig reaction. In Wittig reaction, what is the procedure that would happen is like this. We take you know, I'll write down step by step. PPH3 is been treated with, PPH3 is a nucleophile, by the way. It is been treated with some alkyl halide. Let's say I have an alkyl halide like this, Cl. So what would happen is the lone pair present on this phosphorus would go and attack on this position, try to remove this chlorine out. And as it happens here, so you will get this as PPH thrice positive charge. Correct? Of course, this positive charge will not remain stable for long. That's why to make it more stable, we use a very strong base like PHLi, phenyl lithium. So where you have pH as minus, lithium as plus. So very strong base can extract the proton from this position of carbon because adjacent carbon will get sufficient polarity. The carbon hydrogen bond can be broken easily. Because of which you will get a minus charge here, PPH thrice with plus charge here, which can be written in a resonating structure as a double bond with PPH thrice this way. Okay, this is called phospholide. Phospholide, YLIDE, lide. So you will get a formation of a phospholide. And once you get a phospholide here, PPH thrice, once you get phospholide, now you react this with ketone. Now you react this with ketone. Now basically, in this case, you imagine this way because this was minus part and then we have PPH thrice which has a plus part. Likewise, in ketones also, you can imagine like this, that this part is plus part of carbon and oxygen is minus part. So these opposites attract. This minus will attract this phosphorus. This minus will attract this positive charge. And as it happens here, you will notice that a kind of a transition state is formed here. So we will have, you know, an oxygen present here, which is trying to connect it to PH thrice, which is connected to, this is an alkyl group here, and the negative charge is trying to connect here. Correct? This is the way you can see oxygen and phosphorus will be connected with each other like this. So as they connect this way, now you would see a four-membered transition state is being made here. Okay. Okay. Sorry. So you will see this as a four-membered transition state will be made here. Got it? So as it occurs here, so you will see now this bond will start connecting here. So what do we have? We will get a bond here formation like this with PH thrice and here oxygen made a bond with phosphorus. Okay. And now what would happen? This bond will try to break towards phosphorus and this bond will try to break towards carbon. So that will make it into a double bond formation with this ethyl group. Okay, this ethyl group. Methyl group is there. No? 1, 2, 3. Sorry. 1, 2, 3. Like this. 1, 2, 3. Yeah, this one. Okay. With this methyl group. And the other part which is formed is PH thrice with double bond O. So that's how you will get an alkene formation. As a shortcut, what you can do is like this. This is the shortcut I'm writing. Where there is a ketone here plus PH thrice double bond carbon with some R group here. So all you need to do is remove this group and join the rest. And join the rest of the molecule. So as you join, you'll get this as double bond C with some R group. That's it. Okay. One more group will be here like this. Done. This is a shortcut, and this reaction is called as Wittig reaction. Okay, please check. All okay? Please make a note. Next, let's understand from carboxylic acid how we can get alkenes. We have done this earlier in the form of Kolb's electrolysis for formation of alkanes. There only we learned about this. Let me just give a quick synopsis. So if you have, dicarboxylic salts like CO minus K plus, CO minus K plus, on Kolb's electrolysis, you know that carboxylate will convert into carbon dioxide and give a radical form on these two carbon positions. And those two radicals will terminate to form an alkene. Same logic applies here also. CO minus is there. You can eliminate dot and dot will become a double bond. That's how you will get an alkene form. Okay. This is how you can get the alkene from carboxylic acids. Next is hydrogenation of alkynes, right? If you take hydrogenation of alkynes also, we can get alkenes. But how do we get? Please notice this. If you have a triple bonded carbon and then you react with H2, if you write palladium only, then the reduction will keep on happening till it becomes alkane, But you can stop this reaction from happening when you supply or when you rub the palladium with a barium sulfate powder. When you do that, barium sulfate will act like a poison and this will decrease the activity of metal surface. Okay. And as it decreases the activity, that means it will have less absorption of hydrogen gas. And also, these alkynes are only encouraged to get absorbed up to the formation of alkenes. After alkenes, further adsorption on the metal surface is not observed. Therefore, and both the hydrogens from the metal surface here, like this, they will add from the same direction. That means they both will add from the same direction. That's why the product form is cis here. So you will get a cis form and further addition will not take place. Further addition to alkane will not take place. Hence, you can easily isolate the alkenes from here. The other catalyst which does the similar job is dinickel borate, which we call it as the P2 catalyst. Industrially, it is called as P2 catalyst. Or another catalyst used is PD plus HCl and H2, right? In fact, whether you take barium sulfate or whether you take calcium carbonate, these are called Lindlar's catalyst. These are called Lindlar's catalyst. So Lindlar's catalyst will account for alkene formation and further formation of alkene is not observed. Okay. Therefore, the product formation is always the cis types because the addition is a syn type. The product formation is always cis product. Now, you can make an addition which can be leading towards a transformation. Now, this is a case where the product formation is a trans. Okay, and this reaction is called as Birch reduction. Okay, in Birch reduction, we use either a lithium or a sodium in liquid ammonia. Lithium or sodium, when you add it in liquid ammonia, it will show a stable solution with a highly electron rich solution, a highly electron rich content in the solution. And that will help making this alkyne into formation of alkene. But this time the alkene will be trans kind. Okay. Now, this mechanism is important from advanced point of view, right? So it's better to write and learn everybody. So please, let's look into this, how the mechanism works. And if possible, please try to write simultaneously. See, sodium in the presence of ammonia liquid will release this, you know, two electrons here this way. It will release two electrons in ammonia solution like this. Okay. So as the electrons are released, you will see that these two electrons, I mean, now we have RC triple bond C and R dash being present. So these two electrons will try to go and attack an carbon. Now we'll see, sir, ये already इतना electron density है. How come another electron is being pulled? You know that if carbon possesses a triple bond, its electronegativity is high. Due to its high electron negativity, it can have the affinity towards electrons. And as these electrons approach, this pi bond will shift onto this carbon, the adjacent carbon. So now what you will get is R, C minus double bond C and R dash. This is what you should get. Now notice something here. This R, C minus and double bond C, sorry. Oh, 1 minute, my mistake. I'll start with single electron here. Single electron here, one electron. Yeah, with one electron being pushed. So as one electron is being pushed here, correct? So double bond will shift here and minus charge will come on this carbon. Please check, minus charge will come on this carbon. And because you are pushing a single electron, it will have a radical form. So you will have a C dot with a double bond C minus and R minus. Now if I write this in a hybridized orbital form, you will see carbon having an orbital here with a double bonded carbon which also has one orbital which has two electrons on it. This has one electron on it. And then we have R dash here and R here, correct? This is how it will be. Now, obviously think about it. If these electrons are present, because this is already a pair of electrons. So this pair of electrons and this single electron, they will repel each other. To minimize this repulsion, what will they do? The structure of this orbital will change into this form. This R will remain sp2, pushing the electron, single electron into this orbital, while double bond here, and this orbital will start pushing orbital into a hybridized orbital like this, which are opposite to each other so that they can minimize the repulsions. Okay, this formation is done to minimize the repulsions. And once the electron repulsions are minimized here, now because it has C minus, it will attract the protons present in ammonia. So it will immediately take H plus from the solution and it will now convert into RC with a single electron, double bond with CH and R dash. Okay. So now it has a radical. This is a radical form. Okay. Earlier, what was the form? This is a radical anion form. Radical anion form. Now, once you get a radical form, again single electron which is coming from a sodium can go and attack on this carbon. As it attacks, you will see now it will become R, C, this time with a lone pair and minus charge, and double bond C, H and R dash. This is what you will get. Okay. And once you have that, it will react with H and NH2. So this minus will attack on H plus, bond will break onto this side, and that will make it R, C with H, and double bond C with H and R dash. H and R dash. So what is the product you are getting? Transform. So trans isomer. Now this time you are getting a trans isomer form. Correct? So with catalytic reduction we got cis, with uh, Burst reduction we got trans. Okay, burst reduction is very important, guys. Please check this out. If there is any doubt, you can ask me now. Now, see the next one. You can reduce the benzene also into these isolated double bonds, which means one of the pi bond is being reduced using Burge reduction. See, how does this mechanism works? Basically, on benzene, first you are pushing electrons from sodium. So this one electron will be pushing here, so that will push the electrons away. And then you will get a minus charge here and a single electron here, radical electron. But you know that this minus charge and radical will repel. Now we have an advantage. There is a double bond here which can make a resonance. And due to this resonance stabilization, this will push and pi bond will push here, due to which now the negative charge will appear here, double bond will be here, double bond will be here, and single electron will be here. And this will take, H plus from ammonia, and thus giving you H here with double bond, and single electron. And this radical again will take one more electron and convert into a carb anion. So we will get this as a minus charge. And that can be again reacted with ammonia. It will react with ammonia, and thus you will get this as double bond, and H here. And this is how you will get an isolated double bond form. Finished? The resonance basically helps in pushing away electrons away from each other. That's the reason why we get isolated double bonds. Okay. Now, does the Burge reduction happen on simple double bonds? Answer is no. But if you have a conjugated double bond, answer is yes. Just now we have done it. So basically the double bond will be pushed here, minus will come, and single electron will be here. And both side reduction will take place, and hence one hydrogen would be here and one hydrogen will be here. So this is the product that you will get. Okay. Next. Notice, if in case we have electron withdrawing groups on benzene, right? Like COOR, COCl, NO2, NR3 plus, CCl3, and all of these cases. In that case, the Burge reduction will make sure the addition would happen this way. That means one hydrogen is added here and one hydrogen is added here. Okay. But in case if you have electron donating groups, right? Sorry, electron donating groups here, like CO minus, O minus, NH2, OH, OCH3, CH3. These are all the electron donating groups. In case of we have electron donating groups, then You will have this as ADG, and double bond will form this way. And hydrogens are basically getting added at these two positions. Okay. So without any mechanism, my suggestion is remember it this way, that where the hydrogen is being added in both the cases. Okay. So this is majorly the Burge reduction. Okay. Burge reduction is essential for triple bonded carbons. It is observed in conjugated double bonded carbons, whether it is a benzene system or a normal system. In all the cases, Burge reduction will take place. Now, there is one thing you need to understand, that what happens if you have a what happens if you have a terminal alkyne? Okay. So suppose if you have R, C, triple bond, C and H here, and then you are trying to pull Burge reduction here, that is sodium in liquid ammonia. Sodium in liquid ammonia. Now the problem what happens is sodium, as soon as the electron is released, right? That electron notices that there is a sufficiently polarized hydrogen. It will immediately take that hydrogen away and convert into Rc triple bond C minus, right? That minus will be formed, and then you will see half of H2 will be formed in this case. Yeah, that's how you will get the product formation. Clear? So once you get this form, once you get a minus charge, now it will not encourage to take one more electron on itself. So there will not be any electron that will be coming across this position. So no more Burge reduction will take place. So Burge reduction is going to be negative for terminal alkynes as well as simple double bond formation. Okay, all good, right? What is the stereochemistry of E1, E2? I have already explained you earlier. How does it work? Next. The next part is all about the chemical reactions of alkenes, everybody. So this ends the entire preparation reactions of alkenes. This is the first part of it. The next part is all about the chemical reactions of alkenes. Got it?